is there actually corrosion with regard to stainless steel? Isn't that contradictory? It's certainly not. I will tell you why, and I will tell you how to measure the corrosion resistance of a material in a quantitative way. Actually, we anticipate in pharmaceutical system manufacturing to have no problems whatsoever with corrosion on stainless steel. However, I've been showing you in several videos before, as well in the last one here, that with regard to also carefully made specials, there are corrosion issues that just happen in pharmaceutical environment. And this is a case where you say, okay, corrosion, why does that happen? And I'm using stainless steel, so I can't explain that. So, well, corrosion in general is just something you cannot avoid. Each and every material can corrode. It just depends with a given material only on concentration, time, and temperature. That's it. And so material and the medium has to match to each other. So what is protecting the stainless steel from corrosion? Usually a stainless steel is a material which has at least 10.5% chromium, and this chromium creates a chromium oxide layer which is several nanometers only in thickness. However, this is corrosion protection for the material. So the question is how to determine that and what are the most critical factors with regard to corrosion. As several different kinds of corrosion exist, I would like to pick one which is most important in pharmaceutical manufacturing. This is chloride-induced pitting corrosion. This pitting corrosion will basically tear and pull needles into the surface, holes into the surface, and create non-hygienic conditions and certainly can even destroy the tubing system or the material. However, when we are looking into the facts, you will see with regard to this picture here, you see that chloride-induced corrosion with regard to either 304L or 316L happens already at pretty low chloride concentrations. These chloride concentrations are varying, let's say, in between 100 or 1000 ppm, which is then in return roughly 0.1% chloride concentration. So you can see this is happening at pretty low concentrations already. But what can you do? How can you, let's say, estimate or predict the chloride-induced pitting? This can be done via a empirical method which is called PREN, number estimation. PREN means pitting resistance equivalent number, and this is just a simple, let's say, formula that you can apply to different alloys. The composition of this alloy will give you a number, and with regard to this number you can tell how good your material is in general, how, let's say, resistant it is towards pitting corrosion. A PRN number above 33 is therefore deemed to be seawater resistant. Seawater in general is determined to be 3.56% sodium chloride in water. So that's certainly a pretty high concentration. However, also in pharmaceutical manufacturing, in pharmaceutical systems, also higher concentrations will apply. So that certainly depends on the application. But what can you further do in order to estimate if your material, if your surface as well, is matching to your application? What you can do is to use the parameters that you are having with regard to your medium, and you can apply a test according to ASTM G61. This test is the measurement of critical pitting potential. This critical pitting potential is being done in a 3 electrode setup where you have a specimen with your desired material, and you will dip it into the solution you're actually using. What you're doing is you increase the voltage, you increase the potential, and what is the result is a flow of current, which is certainly initially small, but the higher you crank up the potential, the more current will flow. This will end up, as you can see up here, into a kind of jitter, into a kind of noise that you will see here. And this noise, let's say, is reducing or is resulting from let's say, impurities in the surface, from defects in the surface that will be opened up with regard to this increased potential, and where you have then an initial flow of current, which is pretty high. However, those defects, those impurities will disappear again, and the surface will repassivate. That's what you can see as the current is dropping down again to a certain base level. This number, or this effect, is the critical pitting potential. And the question is, when you use a certain material, when you use a certain surface, then you will get a certain value of it. That is a quantitative value for the resistance towards corrosion. However, what is the sense actually of electropolishing, and how does electropolishing influence this value? Here you can see that an electropolished surface has more than 2 times a higher corrosion resistance value. Here, critical pitting potential value. So you can estimate that you more than double the resistance of your material when electropolishing that. For critical applications, that's certainly, I would even say, a must. However, when you look at that, you can figure that this certainly makes sense. And yeah, I hope I could give you a little bit of insight into the reasons for corrosion, into the basic, let's say, relationships between material, surface, medium, temperature and concentration. And I would certainly be happy if you would address any questions which have left been unmentioned here, that you would address those and let us know, and we would be glad to get in contact with you. Thanks so much. We would certainly be as well happy if you would subscribe to our YouTube channel, and welcome you in one of our next videos. Thanks a lot, take care and stay healthy.